Good morning, everyone. Welcome to a new edition of this colloquia of the research division of the ISC. Today is my pleasure to welcome Pedro de la Torre Luque. Pedro is an early career researcher, young researcher. He graduated in 2021 under the supervision of Nicola Mazziotta in the University of Bari. Before he did his master's, I think, in Granada, and then your undergrad in Malaga. So you're from Malaga, you're from Córdoba. And so Pedro is an expert in, I will say, particle astrophysics, meaning or high energy astrophysics, meaning that he is very well, he does a lot of work on trying to understand the propagation of charged particles in the interstellar and intergalactic medium. So he's an expert in cosmic ray propagation. He is also one of the main developers of one of the main codes in this field that is called Dragon. And in addition to this, something I like very much of Pedro is that besides this, his expertise in astrophysics, so he understood very well the interstellar medium, intergalactic medium, and cosmic ray propagation. He's also good at particle physics. And so he's been dealing and playing with models of dark matter and trying to find indirect searches of these models with indirect signals that could be detected with some of those probes. And I believe this is going to be one of the main topic of your talk. So thank you for coming, Pedro, and the floor is yours.
Well, you have said that it is a pleasure to you to introduce me, but it is a real pleasure to me being here. No, I have seen many things about the Institute of Astrophysics of the Canary Islands, and I really wanted to come here someday. So I have to thank you a lot for inviting me, and to all of you also for listening me in this talk. Okay, I want to speak about an interesting anomaly related to the galactic center that you may have heard about, that is the 511 kiloelectron volt excess. Okay, I will tell you about possible explanations, and especially I will focus a little bit more on dark matter interpretation of this anomaly. But then I will also tell you or discuss a little bit different observables that we can use that are correlated to the 511 excess and that we could use to disentangle between different interpretations, okay? But something, sorry. Oh. Now, okay. Something that I want to leave very, very clear in this talk is that any positron injection in the galaxy will have a correlated distinctive emissions along with them, okay? Here, this is what I'm trying to show you with this sketch, with this figure here, where I'm simply representing the secondary radiations coming from the injection of electrons and positrons from the decay of MEV dark matter in the galaxy, okay? And this and we have these secondary radiations because once you release these electrons and positrons in the galaxy, they interact with the interstellar medium. They interact with galactic magnetic field generating synchrotron radiation at low frequencies, but you also interact with gas in the interstellar medium, producing bremsstrahlung emission that is more important in this energy range, and also inverse Compton radiation from the upscatter of the interstellar of the radiation fields in the galaxy, for example, the CMB, okay? And this is what you see with these black solid lines that are the sum of bremsstrahlung plus inverse Compton emission. And as you can see, they cover a very broad energy range from the X-rays to higher energies, gamma rays, okay? But this is for both electrons and positrons. In addition to this, we have distinctive emissions coming exclusively from positrons. And there are two main ones. The first is this continuum emission that I'm representing as a dashed line here, and comes because relativistic positrons, while they are propagating in the galaxy, they can find electrons in the interstellar medium and annihilate. This is what is called annihilation in flight, and leaves a distinctive maximum, let's say, at the energy of the positrons. So this is a characteristic emission that we can go and look for the origin of these positrons. But then, and more important, perfect for me.
So why do you have a cutoff in energy? Why the
energy. Here, this cutoff at high energies comes because when you annihilate the positron with the electron, the maximum gamma ray energy that you generate is the energy of the positron. Exactly. In this case, this is clear for a monochromatic source of positrons. In the end, in the injection of positrons with a continuum spectrum, you will have a cutoff at the maximum energy, and it will be smoother. You will see these signals later also, okay? But since this is decay, you only generate positrons with an energy, and we have a clear cutoff here. But I will do this broader for all the cases also later. And well, what is more important for this talk, I have to say, is this huge peak or line, as we call it, that is that you see is coming at a very particular energy, 511 kilo electron volts. Okay, this comes from the fact that all these positrons with time, all the positrons injected with time, thermalize. They lose their energy little by little, and when they are thermal, they have a high chance of annihilating with electrons. Therefore, the gamma ray photons coming from this have the mass, an energy that is the mass of the electron, 511 kilo electron volts. And this is very interesting. Exactly. This is gamma radiation. We have the lowest energies to which we have access for electrons and positrons is Voyager, which is outside the solar system. This is not high quality data, let's say, but these are good measurements to even set constraints or try to study the electron plus positron total emission in the galaxy. But actually, these signals are even more effective to probe this kind of electron-positron injections, okay? And this is simply because at low energies, at these MEV energies, you don't have pion production generating a lot of gamma rays. What you have mainly is inverse Compton of cosmic ray electrons. So you have less background, let's say. And this 511 line is very interesting because we have seen, or from the 70s, the experiments have seen a huge intensity of this line, totally unexpected, and that is very concentrated to the center of the galaxy. And from what I have seen, from what I have said just a couple of minutes ago, this is revealing actually a high injection of positrons in the center of the galaxy. More observations reveal that this can be, or this emission in general, can be decomposed in two components. One is what we call the bulge emission, very concentrated around the 8 to 10 degrees around the center of the galaxy, and a more extended and diffuse emission following the disk, what we call the disk emission. And here, for the disk emission, although we didn't predict such an intensity of 511 kilo electron volt emission in the disk, we know some sources that could explain this disk emission. For example, we know cosmic ray positrons, or pulsars inject electrons and positrons. Then we have beta plus radioactive elements that can be produced in supernovae or in massive stars, for example. And this is a clear contribution that we have there. And we know that more or less, some in these contributions, we roughly match the observations, okay? With some caveats, but we roughly match the observations of the disk emission. However, for the bulge emission, we have a problem because we don't have a clearly good candidate that matches the morphology of the emission, or how concentrated it is around the center of the galaxy, and the intensity, the amount of positrons that you have to inject. Tell you a little bit more about this. There are two main candidates, astrophysical candidates, to explain this bulge emission. One is low mass X-ray binaries that was pretty popular and now a little bit less. And this is simply because they are expected to be very concentrated around the center of the galaxy, following more or less the bulge of the galaxy. And there are many models suggesting that they could provide enough positrons. That is, for you to have an idea, is around a few times 10 to 43 positrons per second. It's a lot. Okay? But there are models suggesting that they can provide this amount of positrons. However, these same models predict a lot of positron coming from Cygnus X1, and we didn't observe it yet. In addition, okay, I have to say that these models are very uncertain. And one of the main things that they usually predict is that the positrons will have high energy. And this is a problem, as we are going to see in a couple of slides. You will see why. But the main caveat, in my opinion at least, is that the brightest X-ray binaries have been observed in the disk of the galaxy, and therefore we have problems to reproduce what we call the the bulge to disk ratio, or the morphology of the emission in general. Please.
Yeah. So if you don't mind, so because I mean, Jorge, this is quite new to us. So just to be able to follow the logic of the so if you don't mind, I would like to make a number of questions. So the astrophysical phenomenon, because I mean, due to astrophysical phenomenon, we would expect having a particular line, or we would expect to have a continuum.
Any source of positrons in the end has to generate this line, because simply the positrons will annihilate with electrons at this energy when they have low energies. No,
but we expect the electrons and positrons to have different kinematical energies and so forth. Why they should be annihilating at this particular?
Point here is that these positrons have low chances to interact with any other thing. No, maybe they cross the interstellar gas and they lose energy. With time, they become thermal. So you have almost 95% of all the positrons that you inject become thermal. Okay, and once they are thermal, they remain there for a lot of time, and they will meet at some point another electron, and they will produce this line. So this is a consequence. No, if the positrons are there in the interstellar medium, sooner or later they must meet an electron and produce the line.
So let me phrase it differently, because I'm not a particle physicist. Why? So this energy is a particular energy. Is the energy of the?
This energy is the mass of the electron. So what this, if I can write here, well, simply you have that electron and positron will produce two gamma rays, and if the electron and positron have thermal energies, so the electron energies, they will produce photons with the mass, with the energy of the mass.
Okay, so so in short, any phenomenon, so the annihilation of these two particles have to produce that line. So no matter the origin. Okay.
Whatever thing that it's very, very low. The estimations, you can do an estimation simply from the observations, and it is 3 to 5%. So actually 95 or plus are going to I will use yeah. Thank you for the question, because I didn't know that it wasn't clear. It's a very good point. So yes, this is a consequence of whatever scenario that is injecting positrons in the galaxy, okay? Then, as I said before, we have a guaranteed contribution of positrons coming from beta plus radionuclides, no? Or said in other words, these radioactive elements synthesized in stars, for example, aluminium-26, that decays in producing magnesium plus positrons, okay? And gamma ray lines also. Okay, but this is another thing. And here we know we should have this contribution from massive stars. We expect them also to be quite abundant around the center of the galaxy, in the bulge of the galaxy. Here you can see this peak. And then a good thing is that the analysis of the morphology that we are going to see with more details later support or favor the idea of positrons injected with a few MeV, not very high energies. And this is good, as we are going to see, okay? The only problem is the real problem. We didn't observe enough massive stars in the center of the galaxy to explain such an injection rate that we need to explain the 511 kiloelectron volt line.
Have you ever seen positrons being emitted by luminous low mass X-ray binaries? Because you said that Cygnus X1 is not, so it's just not clearly.
But then a reanalysis wasn't clear. So not directly. So this challenges also this scenario. Okay. It is more, right now it is more clear, but there is a debate. No, nothing known of this are discarded, nor exactly. Yes. But here we can have other possible explanations. More exotic maybe, but the fact is that people realize that this morphology of the 511 kiloelectron volt emission could be the same morphology as you expect from positrons coming from annihilation of dark matter following a Navarro-Franken-White distribution. Or said in other words, this morphology, these green lines here, follow perfectly the distribution of dark matter squared, because annihilation is proportional to raw dark matter squared, and for a Navarro-Franken-White distribution, that is a prototypical dark matter distribution.
But that is very likely the most direct evidence that this is not dark matter, because the analysis of the velocities of the galaxies suggests that the center is not dark matter dominate, and they are core also because of all the feedback effects and so forth. So the Caspi Navarro-Franken-Whites are basically ruled out, no, from the yeah, no, on the contrary, for the most massive is where you can rule it out. So you can explain the rotation curve towards the center without too much dark matter. So the problem is appearing in the out. I think, I mean, as far as I can, as far as I know, that it could be very little. The central innermost region of the most dominated baryonic, I mean, like the Milky Way. So you can explain the dynamics with its own baryonic content, let's say.
From what I know, these simulations usually are good at inferring the distribution of dark matter above 3 kiloparsecs. So they are usually more or less good to know the dark matter local density. Yeah. But actually, these things grow to the center as a kind of power law, no? Going to an index, gamma. Mm-hmm. This is another point that I'm going to comment later. Yeah. But I mean, from my conversations with the people doing this kind of simulations, it is still the midpoint, the Navarro-Franken-White distribution. You could even have something Caspier than it. It's true that in dwarf galaxies, mainly, they favor something more chord, no? Something flatter. Not from one I have. At least from what for example, Fabio Yocco and these works, they say that in the inner galaxy, you support much Caspier profiles and less Caspier profile. For example, this can be related to the galactic center excess. Yeah. Okay. Yeah. So the point is that they saw this coincidence. Yeah. Sorry. We will try to use the mic more. Mm-hmm. And this was like a motivation to propose sub-GeV dark matter as a possible explanation of the 511 kiloelectron volt excess. Here, they easily saw that this works for Caspi profiles, but for annihilation, but for decay, the profile that the morphology of the emission that you expect is too flat to reproduce the 511 kiloelectron volt morphology or the concentration in the center. And something similar happens also for P-wave annihilation dark matter. So velocity dependent annihilation. Okay, that is another process that can be there. And here, well, you may, this is sub-GeV dark matter, what was proposed. That is not like the typical WIMP, no? But there are many possibilities. You can have what is called asymmetric dark matter, you can have a scalar dark matter, or you can have even dark matter going to a hidden sector and then coupling to the standard model. So there are different particle physics models that can explain dark matter having masses that are below the GeV, okay? And these all have a common thing, a common constraint, that is that to be compatible with cosmological constraints, Big Bang nucleosynthesis, and cosmic microwave background, they must have masses above a few MeV, I would say, okay? But for sure, we could try to narrow a little bit more the parameter space of possible dark matter candidates by studying the emission of positrons and electrons, because, as I told you, they will propagate in the galaxy and their propagation will be directly linked to their energy, okay? While they are propagating in the galaxy, they will interact with the interstellar medium, producing observable radiations that we could observe, okay? The usual way, or one way at least, to study the propagation of electrons and positrons from the annihilation of dark matter, and one thing that I have to leave clear here is that in this process, direct annihilation of dark matter to give positron electron, the energy of the positron and electron is the same as the mass of the dark matter particle, okay? And this is an important point that I didn't make before, sorry. So, okay, to study the propagation of these positrons and electrons, we usually make use of this diffusion equation, which has basically 4 terms for our purposes here, at least. The injection of positrons, that in this case is following the dark matter distribution, the term of energy losses, which basically accounts for, at low energies at least, charged particles ionizing the medium, that is giving energy to the medium, losing this energy, and this is more efficient as the energy of the positron or electron is lower, so you lose energy quicker as you have less energy. And then we have the diffusion coefficient, that is a key parameter here, and it is usually parameterized as a power law or modified power law in energy from cosmic ray observations. What is the problem here? The problem is that we don't have good cosmic ray observations below some tens of MeV. Therefore, to do these estimations of very low energy positrons and electrons, we have to extrapolate our let's say, models that are tuned to higher energy cosmic rays. And finally, we have this term here that basically accounts for reacceleration, the exchange of energy of low energy particles with plasma waves, okay? As you will see, this can be important for very low energy positrons. You can have a subtle boost on the energy of the positrons that you inject, okay? And taking all of this into account, we obtained what we expected, actually, that the higher the energy of the positrons, or said in other words, the higher the mass of the dark matter particle, the more the positrons propagate and the less concentrate they remain around the center of the galaxy. This is what is shown in this plot, basically, where this black line represents a mass of 1 GeV, the blue line 100 MeV, this green line 10 MeV, and so on until 1 MeV for the cyan line here. And as you can see, an important consequence of this mass-dependent morphology is that only positrons that are injected with a few MeV energy, or coming from MeV dark matter masses, will closely follow the initial distribution, the Navarro-Fredkin-White, or the distribution of dark matter with which they were injected first. This is an important consequence. And the second one is that since we have these constraints coming from cosmology that only allow us to have masses above a few MeV, we may actually need something caspier than a Navarro-Fredkin-White profile. And this is something that is important because there is a subtle trade-off between the distribution of dark matter that injects the positrons and then how much they will propagate, okay? But this actually narrows down the possible masses that we have, okay? Saying that we need at least, at most, positrons injected with MeV energies, or MeV, tens of MeV, with tens of MeV positrons and masses of tens of MeV, okay? The caveats here that I mentioned are simply because, okay, we are using an extrapolation of the diffusion coefficient that we know. This is an estimation, and diffusion at these regimes, at very low energies, is quite difficult. So the best we can do is to put the most pessimistic uncertainties in our estimations, so assumptions in our estimations, and try to assess all these uncertainties, okay? But the argument that was harder, let's say, for the dark matter hypothesis was what I was explaining before, the in-flight positron annihilation emission. And the reason is simply because the higher the energy of the positron, the higher is the signal that you expect, and also extends to higher energies, okay? You can see here in the left the trend for different masses of dark matter injecting positrons and electrons directly, and you can see how it grows for higher dark matter masses or the same higher positron energies, okay? And this turns out to be a problem because when you compute the total flux that you expect to match the 511 kiloelectron volt observations, you see that these gamma ray signals exceed the data above around 5 mega electron volts. And this is imposing a very strict, let's say, constraint on the mass of the dark matter particle that is injecting the positrons. And this means that we have a huge tension with cosmological observations. So this, in fact, killed, say, the dark matter hypothesis for some time. But there have been ways to avoid this constraint, or at least to relax it a little bit. One of them is a recent idea that we had. Exactly. So, but you have the constraints from big bang nucleosynthesis and CMB that doesn't allow you to be compatible with these observations. You need masses above a few MeV. So it's like an overlapping constraint, let's say. So this is very important. And in fact, it was taken as a serious concern for the dark matter interpretation, and it must be taken as a serious concern. But there are ways to avoid it, no? One of them is simply to have dark matter not directly annihilating into electrons and positrons, but having mediators, and then these mediators producing the electrons and positrons. This is a general idea. In the end, the final positron will have a lower energy than the mass of the dark matter particle because you have particles in between, let's say. And this is what we used, but applied to a specific case. We found that assuming a fermion that couples to axion-like particles, we can reproduce or we can match the dark matter abundance today for cross-sections that are actually what we need to reproduce roughly the 511 kiloelectron volt excess. The 511 kiloelectron volt excess. To give you some more details, here, this kind of scenario is dominated by annihilation into two particles, p-wave annihilation, in the early universe. But when let's say, closer to the present, when the velocities are lower, the S-wave mechanism dominates. So you are producing 3 axion-like particles in this decay, and each of them will produce electrons and positrons. This production of 3 bodies, in the end, leads to not a unique energy of the positrons and electrons, but a continuous distribution of the positrons of electrons, okay? Because we don't have this two-to-two process, okay? And this means that in the end, depending on the mass of these axion-like particles, for which we have some freedom, let's say, in the constraints, you could have, for a 10 MeV dark matter particle, a maximum positron energy of even 3 mega electron volts. Therefore, evading the constraints because you are injecting lower energy positrons, actually. Okay. And the direct result of this is that these in-flight positron annihilation signals are reduced, and you are allowed to have masses of up to around 15 mega electron volts in this scenario. Okay. For you to have a direct comparison to what you would expect from direct production annihilation into electrons and positrons, you can see in the right the comparison with the orange line, that is direct annihilation of electrons and positrons, with this model that is the black dot line here. And you can see how a 10 MeV mass was really ruled out by COMTEL observations, while now this 10 MeV candidate that doesn't suffer from the problems with cosmological constraints is still compatible with at least MeV gamma rays. The mass of the MeVs, we can regulate it, but it's between 2 MeV and the mass of the dark matter particle. In this scenario, we consider, and I think it is dominant by at least 3 orders of magnitude, the 2e plus e minus. Then having 3 orders of magnitude emission, we took into account the inner Bremsstrahlung emission, and was even more important than this other gamma production. But even the inner Bremsstrahlung emission was much lower than the one from in-flight positron annihilation. Good question. And well, finally, the final point here is that the predicted cross-sections, because to explain the dark matter abundance today, you get a number of the cross-sections. it allows us to fit well latitude and longitude profiles of the 511 line for a roughly Navarro-Frank-White distribution of dark matter, making this scenario a viable possibility at least, okay? But you may wonder if there is still any possibility for direct annihilation into electrons and positrons, and the answer is yes. And in particular, we were working on a specific case that was related also to one of the previous questions. And here what we used is dark matter spikes. And what are dark matter spikes? Are simply very high concentrations of dark matter around Sagittarius A, in this case, around black holes in general. Since these black holes have attract a lot of, let's say, dominate the potential, the gravitational potential, dark matter particles tend to concentrate a lot around the black hole, in this case Sagittarius A, in the center of our galaxy. The result of this is that you have a very high concentration or very high amount of dark matter very close to the black hole, and this is what we call dark matter spikes. This is something that can be observed in other black holes, not necessarily only in the Milky Way, okay, in Sagittarius A. And the point here is that this scenario would produce a huge injection of positrons only in the bulge, while a negligible emission far away at high longitudes, let's say, okay? Because you have a lot of dark matter very concentrated in the center of the galaxy, you need very low cross sections for this, and you are not producing a lot of, you are producing negligible amount of positrons far away from the center, okay? So with this possibility, we needed something to reproduce the disk emission that we observed with the detectors. So our hypothesis here was that massive stars are dominating the disk emission. They inject enough positrons to explain the disk emission, something that is reasonable, while the bulge emission is dominated by this dark matter spike, okay? And in the end, again, we could reproduce well with different spikes models, the dark matter, the 511 kiloelectron volt signal. And also, this allows us to relax the constraints from diffuse gamma ray emissions, because now we need lower cross sections, and second, we don't need dark matter to be responsible of also the disk emission. So there are other sources taking care of the positron injection of the disk emission. And the good thing of massive stars is that they inject low energy positrons, and therefore they don't produce, or we don't expect them to produce high diffuse, continuum gamma ray emissions in the MEV. Therefore, in the end, what you see in the right is that the mass limits from gamma ray observations can be mitigated, and we could have in this scenario masses of up to 20 to 30 MeV, which is much bigger than the initial window, no, that we had before. Okay, this is interesting, but here you may see that for all these models, for different masses, we need to have a contribution in the diffuse gamma ray emission. We need a signal coming from positron in-flight annihilation. This is a direct consequence of these dark matter models, right? And this may be a problem, because if we don't see any feature of this, is it really possible? The point is that there are a few papers claiming that there is an excess in the observed MEV emission that could be a direct indication of these positron in-flight annihilation signals. This is where, for example, one of these models. This okay. In this figure in the right, I'm representing, or I'm taking one of the evaluations from a paper where you see the inverse Compton emission, the total inverse Compton emission, that is the black line, and its different contributions, because inverse Compton comes from upscattering of starlight, infrared light, and CMB in the interstellar medium. Okay, and as you can see, these predictions are around a factor of something, no, even a factor of 2 lower than what we observe. For some people, this was taken as an indication of the injection of high energy MEV photons. Okay, but one has to be honest, and not all the models tend to see this excess here. For example, you can have a model which is compatible with higher energy observations, so cosmic rays, Fermi-Lat gamma ray observations, but also compatible with, as you see in the left panels, the MEV gamma ray emission. But something happened here that is interesting, and it is that when we were looking for more data closer to the galactic center, because naturally, if the 511 kiloelectron volt line, or sorry, if these MEV photons come from dark matter, we expect them to be or we expect signals to be more intense towards the center of the galaxy, right? So we were interested on looking for windows that are closer to the center of the galaxy. The problem is that MEV observations are quite difficult, so we don't have many, okay? But what we found when we were a little bit closer to the center, in the right panel, is that there is a bump-like excess, no? Or something that we weren't able to explain with the same models that explain quite well the diffuse emission in other windows, okay? You can see this in the right. We can, our model, it goes well at lower energies, or okay, at least, and at higher energies, but in the middle there is a kind of excess that we weren't able to explain. And the point here is that this excess can be very well reproduced when you add the signal from a 17 MeV dark matter particle explaining the 511 kiloelectron volt excess. So here we could have a correlated feature that would be a smoking gun for a dark matter related injection, okay? What is the problem? What is the problem? The problem is that the significance of this excess is pretty low. You can see the error bars that we have here. It's 2 point something sigmas. So this is at most a hint, okay? But at least tells us how interesting is to have more data and better data towards the center of the galaxy, okay? So trying to pursue this, no, having some observable around the center of the galaxy, we realized about another interesting anomaly, actually in the very center of the galaxy, that is an anomalous ionization in what is called the central molecular zone. Central molecular zone is basically a huge gas structure, mainly made of hydrogen, molecular hydrogen, that has these dimensions that you can see here, and is very abundant in molecular gas, okay? Hydrogen mainly. And the point is that while cosmic rays that are expected to be the main ionization agent in all the galaxy are only able to, or are able to produce ionization rates of the order of 10 to minus 18 second minus 1 to 10 to minus 16, roughly, second minus 1, the amount of ionization that we observe here, the ionization rate, is huge, around 100 times higher than what we can do with cosmic rays, okay? For sure, this is not totally understood because the dynamics of cosmic rays within molecular clouds is quite difficult, okay? But but there are plenty of works clearly pointing to an anomaly that cosmic rays cannot explain. For sure, there have been some proposals, no? Diffuse cosmic rays, Sagittarius A star, point-like sources, because we have observed powerful point-like sources, like this one observed by Hess in gamma rays. But they all fail, okay? And let me explain you why. Basically, what we need here is a source of positrons that is quite concentrated around the galactic center. Otherwise, we could have observed, for example, bremsstrahlung radiation farther away, okay, in other regions. And by the same argument, more or less, we need also a source that is injecting low energy particles, because otherwise they would escape. These electrons and positrons could escape, and you could potentially observe synchrotron radiation, inverse Compton, bremsstrahlung. And as I said before, no, low energy is required because as you have lower energies, you thermalize or you lose all your energy quicker. So you remain within the molecular, in this case, within the central molecular zone. So in fact, here, you have to make your positrons die, let's say, or provide their energy into ionization very quickly. And the final argument that is ruling out point-like sources like Sagittarius A star, for example, is that the observed ionization profile is very flat. So whatever is causing this ionization is very uniformly distributed within the central molecular zone. And this is something that, for example, Sagittarius A star fails to reproduce, as you can see from these lines here. Therefore, we need something diffusely distributed, and we wonder if dark matter can do this job. What we found here is very interesting. For very low cross-sections, these cross-sections that you see in this panel are around 5 orders of magnitude lower than the current constraints, you could reproduce or explain the ionization rate observed in the central molecular zone with gaspier than Navarro-Frankel-White profile, okay? But you can relax this with the cross sections because the current constraints are quite, let's say, weak right now. A question?
You can correlate that thermal cross-section with the one that you need for thermally producing the dark matter at the early universe, right? So the model can connect the 2 points, right?
In a second. Thank you. Yeah. Yes. And in fact, something that we found and wasn't investigated before is that MEV dark matter is a very efficient ionizer if they are injecting electrons and positrons. These low energy positrons and electrons that you are injecting basically lose all their energy, deposit all their energy into ionizing the central molecular zone. Okay? So these are very efficient ionizers. And this is true for the central molecular cloud, but also the central molecular zone, and also whatever molecular cloud in the interstellar medium, okay? Okay, the other important feature that I was talking about is that the observed profile of the ionization is very flat. And in fact, from our simulations, taking into account the uncertainties in diffusion, these bands here represents optimistic and pessimistic scenarios of diffusion, but in all these cases, we still get something that is more or less flat. So in agreement with the observations. And what is the important point here? I think there are 2 important points, okay? This MEV positron injection would be undetectable from inverse Compton, bremsstrahlung, or synchrotron, because you need cross-sections that are very, very low. So this will produce negligible secondary emissions, let's say, and something that is even nicer and goes to your question. It seems.
Bremsstrahlung emission here. So Bremsstrahlung is a thermal Bremsstrahlung or?
Yeah, radiation, no. But the amount of flux, the total flux that you need, is so concentrated there that you couldn't observe with the current observations any Bremsstrahlung, inverse Compton, or even synchrotron emission. And the very important point, in my opinion, here is that the same cross-section, or the cross-sections that are needed to explain the 511 kiloelectron volt excess are exactly in the ballpark of the cross-sections that we need to reproduce this anomaly. And this is important, but it can be extrapolated not only to dark matter. It means that maybe, or probably, and I will go to that a little bit later, whatever is the source of the 511 kiloelectron volt excess is also responsible of this ionization, or at least a very important part of it, okay? And this is a quite meaningful thing here, okay? These observables are totally correlated, but this is true not only for dark matter, but for whatever source that can be producing these things. I'm gonna go fast. Okay, just I was quite interested, no, in looking at these signals of dark matter injecting electrons and positrons in the galactic center. This is what you see in the left, okay, in the inner 100 parsec. And the point here, what I found is that even for very low cross sections, you would inject more electrons and positrons from dark matter in the center of the galaxy than what you expect from different background models. This is what you see in the right, okay? Just to give you some quick information. This second peak here refers to reacceleration, okay? This exchange of energy with the plasma waves with the positrons can create a population at higher energies, but it is not dominant, okay? The important point for me is that the current constraints allow this dark matter to produce much more electrons and positrons than what you expect from cosmic ray electrons, no? And pulsars also. And this is important because one can wonder what happens is if actually MEV dark matter has some role in regulating the star formation at the central molecular zone, okay? Because these gas clouds are actually where these stars are born, no? Or what happens if we have this MEV dark matter and it has and plays an important role in the chemistry of the central molecular zone? I think, well, this is much about what we can do right now, no? But I think this is very intriguing, or at least for me, it's a nice possibility that is open, no? Just very quickly, to be complete, I want to show you what are the current constraints, more or less. We have constraints coming from direct observation of electrons and positrons at around tens of MeV from water. We can have constraints from X-ray and gamma ray measurements from this same inverse quantum mechanism. People have used gas heating and ionization to put constraints, but among all these procedures, let's say, or probes, the CMB constraints are by far the most robust ones, okay? Different constraints usually have come with different assumptions and uncertainties, but the CMB constraint is quite strong and robust. So if one has to rely on one of these, CMB.
By CMB constraint, you mean energy injection from late annihilations of keV.
Yeah, thank you. And among all of these, we have also very powerful constraints coming from.
Back to the CMB. The constraint is from the spectrum, black body spectrum, or from the angular power spectrum? You affect, okay, from in the, okay, at early ages, high redshift.
And the observations of the disk emission far away from the center reveal a low, let's say, positron injection, and therefore we can use these high longitude observations to put constraints also from the 511 kilo electron volts, okay? And therefore we can place very strong constraints, but with high systematic uncertainties from the 511 kilo electron volt line. High systematic uncertainties mainly because the observations of the 511 kilo electron volt line far away from the center are extremely difficult. No? This is a really difficult experimental task. And well, before leaving totally the central molecular zone, I want to tell you about an ongoing project in which I'm trying to study what is the ionization that can be produced from massive stars in the bulge. Okay, basically, I'm putting massive stars distributed following a bulge distribution. That is what you can see in the right, where the different colors indicate different heights from the galactic plane, from the galactic disk. And to mimic a population of massive stars, I'm injecting these positrons following a log normal distribution in energy with a central energy of MeV. Okay, these energies is what you see in the left plot here, and basically this is the injection spectrum of positrons from these massive stars. And here, to be consistent, what I'm doing is to normalize the injection rate to that is reproducing the 511 kilo electron volt observations of the bulge. That is a few times 10 to 43. Here I'm using 2 times 10 to 43. And the point is that we observe that depending on the energy of the injected particles, we could, first of all, produce much more ionization than cosmic rays. And second, we could be compatible with the central molecular zone ionization. And also the spectrum, the profile that we expect is very flat. That you can produce aluminum-26 radionuclides, for example. Wow, this is a good point. Maybe tens of solar masses? I would say so. I'm not an expert on that. I'm not an expert on that. But I don't know what is the threshold to go beyond silicon. That is what you need. No, beyond carbon, oxygen, CNO.
Have this kind of populations in the center of the galaxy because they will live very short, no? And the populations are very old. So.
Yeah. Yeah, it's true. And this is the main caveat for this explanation of the 511 kilo electron volt line. However, it's true also that they emit a lot of ultraviolet light, no? And this ultraviolet light is very, very quickly absorbed in the gas, in the medium, in the central molecular zone. Therefore, maybe they are very difficult to observe. So this is the debate that is right now going on. Okay, since I have 1 more minute, I don't have time to speak about other ways to probe exotic mechanisms of electron-positron injection. But believe me that with the 511 kilo electron volt observations and this continuum diffuse gamma ray emission, we can consider a lot of exotic scenarios. I wanted to talk a little bit about low mass asteroid mass primordial black holes that are quite interesting, and they would emit electrons and positrons via Hawking radiation. Okay, simply you can see this is the 511 kilo electron volt line that we would expect, morphology that we could expect from evaporating primordial black holes. It is roughly similar to what you expect from decaying dark matter. And then going to more exotic scenarios, you can also place or probe, no, let's say, constraints on the injection of electrons and positrons from axion-like particles, sterile neutrinos, dark photons, or other feebly interacting particles that are produced in supernovae. In general, supernovae reach very high temperatures, so you can thermally produce these light particles very abundantly, and these particles, if they couple to electrons and positrons, they must decay into electrons and positrons out of the star or the supernova, injecting a lot of electrons. Okay, well, sorry. Just simply saying, oh, okay, perfect. I think this anomaly deserves more attention because it has a big, a nice phenomenology, no, behind it. No, you have many correlated signals. If it is dark matter or if it is something astrophysical, you can see correlations in different observables, and this is quite interesting. And well, since well, you can ask me whatever you want, I'm very happy to discuss.
Thank you, Pedro. Let me start with Alicia, because Nacho already has asked many questions.
Thank you for the presentation. Actually, I want to recover the topic on the microquasars, because now we know that microquasars are persistent sources of very high energy gamma ray emission, and that they even emit PeV gamma rays, which means that you can have like PeV protons in this case. But of course, there can also be we also know that they accelerate electrons up to and for example, I'm thinking specifically most of the microquasars that have been detected, of course, they are in the galactic disk. But for example, we have a V4641 Sagittarius that is indeed in the galactic bulge direction, and this source emits PeV gamma rays, photons. So could this be still compatible with the
Thank you very much. No, microquasars are in fact another possibility, but I think both the models and the observations are still a little bit premature to put them as a firm candidate. Microquasars are super interesting. In fact, as you say, no, they can be a new population of gamma ray sources that can explain the high energy photon emissions. Maybe also even can have a role in neutrino production. The only point that I see that can, well, first of all, we need to observe more of them, many more of them. And then we need an estimation of the low energy positron injection, because that is the key point here. Anyway, they could be a very relevant fraction of the total disk emission or the bulge emission. And they are interesting, but still the other possibilities seem closer a little bit, but for sure is another compelling candidate.
Okay, thank you.
Nacho?
So I have done very few questions compared to the ones that I can make. So, okay, so just to start. So if I understand your model correctly, the dark matter is decaying and is decaying continuously, right? And it's not produced again, or?
Yeah, well, okay, this is the standard paradigm, no? Dark matter, in the scenario that can explain the 511 kiloelectron mole morphology, it's annihilating continuously. But annihilation goes in a rate that is so low that in the end it doesn't affect hugely the amount of dark matter that you have.
No, so
but
you would expect to find more dark matter the early universe, all right? So because I mean you are continuously
sure.
And right now you are even suggesting that the distribution of dark matter is even more peak than in Navarro-Frank and White.
It could be.
Yeah, but I mean, even, you need the Navarro-Frank and White at least, no?
No, yeah, in that respect, something interesting is to try to observe 511 kiloelectron volt photons that are redshifted, no? That comes from early epochs. The problem is that it is more challenging to do this.
I'm trying to understand the logic of the model. So if I go to high redshift, I would see even more dark matter, more peaked, right? Is that correct?
Well, when you go to to high redshift, you go to extragalactic galaxies, no, to other galaxies,
Yes.
no more than here. Well, yeah, you will have more dark matter at some point, but I don't think
So you don't have a number in the top of your head like, okay, at redshift 2 we have 2 times more dark matter or things like that. You don't have so you don't know the. It's just to understand if that is compatible with what we observe, which is goes more on the line that the amount of dark matter in the most massive galaxy at high redshift is less. So it's just to understand the logic. So
exactly. Yeah, it is redshifted. Yeah, no, absolutely. And probably there are other difficulties. No, it is important to say that this 511 kiloelectron volt observation is super difficult. So it is already a lot that we have observed it clearly in the disk of the galaxy, and we are close to observe other galaxies. To go to even lower intensities, like to go to redshifts that are higher, it's going to be very challenging.
and also while you were talking, I was checking about the presence of cores by other by other probes. And in fact, it seems that the community agrees that the center of the Milky Way has a core on the dark matter distribution. I mean, using microlensing and other dynamical probes. So, it would be really great to see how this model, if it's not in conflict with other distribution.
In fact, when I have asked my colleagues working on that, for example, Fabio Iocco, who is one of the main researchers on that, no, they all agree that you have, what I wanted to write before here, if you have this gamma that is like the index on which you are, the slope of that indicates the concentration, you have something that can be between 1.3, 1.4 even, to below 1, something below 1, okay? Below 1 would be in something core, more than 1.4 would be something very custom, okay? And in fact, for example, there is another anomaly, the galactic center anomaly, and for that you need a profile that is with a slope of 1.2, 1.25. And this is broadly in agreement with
Okay. More questions or comments for Pedro? Have 2 plus 2 ones. First by Andres.
So do you know that we can detect similar excesses in, say, dwarf galaxies, or is the data there, or where you don't have the complicated baryonic physics and you could have cusps or no?
I think it would be difficult. Depends on. I mean, here what you need is a huge injection of positrons, and you have some gas where they can annihilate with the electrons. So in principle, I would say that the more gas you have, the better. No, and the more if you see that you have microquasars, you have other interesting sources that are related to positron injection, it could be interesting. The problem is that right now these detections are so difficult. We should go to things that are close to us and that are exceptionally bright first.
Okay, thanks.
Last question by Carlos, I think, or no?
I'm just trying to, sorry, I have to leave now. Thank you so much for your summary, for your talk. I'm just trying to summarize the things you've been mentioning, putting aside the exotic scenarios that you were mentioning at the end related to primordial black holes of asteroid masses and so on, and strictly to dark matter decay. You said that, on the one hand, the CMB observations on big bang nucleosynthesis need high MEV, right? Exactly. Which are, however, discarded in the standard, decay, in the direct decay by observations in this domain. The model you have been advocating for is that you always need to have an intermediate particle or something, right?
Not in the case of spikes.
With the exception of the spikes, right? So I wanted to insist on this. So the spikes are just simply point-like objects, events that happen in the bulge, right? And in that case, you would avoid this limitation.
Yeah.
You could have a direct decay from dark matter
Exactly.
to this
There are other models, no? There is a third model that is in elastic dark matter, in which dark matter has like atoms, no, levels of energy, and they can be excited and de-excite, producing electrons or positrons. That
Okay.
is another hypothesis, because
Another
you could produce low energy electrons,
Okay.
and there can be more. Actually, there can be
I'm sure.
more
Okay.
theoretically, but these are all only arguments to say, okay, this bound that we thought it was totally robust
It's
can
not-
be
yeah,
avoided
can be
in different
relaxed,
ways.
yeah, somehow.
And,
Thank-
I would say, what for me, my main take-home message here is whatever is causing the 511 kiloelectron volt emission will have different correlated signatures that we could start look for them, because we already have observations.
Gracias, good.
Okay, let's thank Pedro again for his nice talk. Just to inform you that he's going to be here until the end of the next week. Okay, so if you have questions or comments, if you have many more discussion, he's in front of my office.